Welcome everyone, and thank you for joining me today for our professional development hour. My name is Corey Hietola. I work for ThermoTek, and I will be going over the differences between dedicated outdoor air systems, or DOAS, and RTUs, or the traditional rooftop units, and how they are, and how we need to meet the changing needs for modern building HVAC design. So today's goals, we're gonna start off by reviewing the traditional mechanical HVAC design and understanding the primary needs for HVAC equipment. Then we'll get into the challenges and status quo on for existing equipment faces, or challenges that existing equipment can face within buildings with the increasing ventilation needs and filtration requirements, while also maintaining the comfort in a cost-effective manner. And then finally, we'll discuss the advancement of DOAS technology and how DOAS can meet these changing needs while offering an affordable and sustainable solution for buildings as we get into the future. If you have any questions, feel free to enter them into the chat, or you can email me. My email is corey.hietola@thermotek.com, and we'll get back to you either in chat or via email once we are done. So to start a traditional building HVAC design, there's typically some primary objectives. The main one is maintaining a comfortable space temperature and humidity, while also making sure that you are providing a proper amount of fresh air to ventilate the space and meet in any outdoor air ventilation needs. And then also providing clean filtered air that is free from contaminants with any of that outside air that is being brought into the space, or any of the return air that is being recirculated into that space. So traditional building HVAC design, typically, or how it's been done for decades, is using rooftop units, or RTUs. Majority of the time, these primarily use only recirculated air from the space, and they're basically just a metal box that will bring in return air through some return duct and then discharge it at a fixed temperature into the space. Typically, these operate in a fixed on or off position. They don't really have any modulation. They're just looking at the space needs and whether there's a call for heating or cooling from the space, and then they'll cycle on or off based on if that space has any need for that heating or cooling. Most of these have very basic filtration, so you aren't getting very high levels of filtration for that recirculated air. Oftentimes, these are only operating based off of a space thermostat and are not looking at any humidity, or I guess in this case, since it's mostly recirculated air, any intake air coming into that unit. And then it'll only cycle based on whether it is needing heating or cooling for that area. So with the introduction of ASHRAE 62 and 62.1, there really began to be a highlight for outdoor air ventilation needs for spaces in order to maintain an effective comfort within that space. And as it started to become more mainstream, we started to face additional challenges with bringing outdoor air into these traditional rooftop unit systems. Some of the main challenges that we started to see is that a lot of these aren't really meant to handle outdoor air loads, since they are only designed to operate based on recirculated loads for the space to meet those space requirements. Somewhere around the 1970s to the 1980s, that's when this practice kind of began to be introduced, but the equipment didn't really exist yet that could properly handle those outside air loads. So they began to just traditionally introduce those into those existing rooftop units, which aren't necessarily designed to meet those additional outdoor air loads. So the way they started to do this with the traditional rooftop units is they incorporated an outside air damper, and they would bring in very small amounts of outdoor air to meet the building ventilation needs. But the rest of the system primarily remained the same. So it's still operating based on the same space thermostat, just calling it on or off. So whenever the space is satisfied, those units are typically in an off position. So anytime that the space is not calling for heating or cooling, that's when you can start to face challenges because that outdoor air ventilation is no longer being brought in. Since the majority of the components did remain unchanged, the unit design was still mostly designed around handling only those space loads and not necessarily taking into account those additional outdoor air loads that are now adding more air for the unit to process that isn't really at those return conditions. You're now looking at a wide range of outdoor air conditions. So here is a typical schedule that you'll see for traditional rooftop units that are using some amounts of outdoor air to meet those building ventilation requirements. Oftentimes you'll see these where it'll be anywhere from 15 to 20 to 30% outside air, and then the rest will be return air. But once again, the issue with these is that these RTUs are not designed to process that outdoor air load, even though they're being tasked with being able to handle that. So this will oftentimes result in a number of issues being introduced into the buildings that are still being dealt with today, because this is still a very common approach to incorporating building ventilation and using RTUs with outdoor air loads. So here's a picture of, I guess, where you'll see most of those, I guess, sensible or latent loads based on typical outdoor air conditions for places around the United States. And if you look, majority of the time, the primary load is from the latent load or the humidity that the system needs to take into account, and not necessarily the sensible load. So if you're looking at a traditional rooftop unit system, without getting into too much details here, you can see that typically you're only looking at the return conditions, which are in the green dot on the cycle chart here. And what they're going to do is they're going to cool that air down to a saturated point, and then continue to cool it down to around a 55-degree saturation temperature that will then be discharged into the space. But the problem with this is that when you start introducing outdoor air loads, there isn't much humidity that is being taken out of this, because you are only looking at the sensible load, since that's what these traditional RTUs are designed around. So if you look at the red dot if we start to introduce a small amount of outside air, then we get down to the mixed air temperature, which will be the orange one. And it doesn't seem like it's much difference for what the system has to handle. But if you look, as you start to get to that saturation point, you have to cool cool down to a much lower temperature, or you have to a little bit more than if you're only looking at the return temperatures, which oftentimes will lead to oversizing a system in order to meet that. Or if you are using the typical approach without increasing the size of the RTU, then you're actually not cooling that down to as low of a saturated temperature. So you're not taking out as much moisture from that system as you would if you're looking at only the return air temperatures. So this can end up leading to discomfort or humidity issues inside of the space, because you aren't able to take into account that extra latent load from introducing even small amounts of outside air. So if we look at an example, we'll take a 2000 CFM supply, and we'll look at both 0 CFM of outside air, and about 28% outside air. And in this case, we'll look at Charleston, South Carolina. And as you can see, we'll have the ASHRAE design conditions. And in this case, we'll use the 0.4% ASHRAE design conditions. And what this means is that only about 0.4% of the time during the year, these outside air conditions will be outside of these peak conditions. So in this case, if we're looking at the 0% of outside air, so everything is returned for a traditional RTU system, you only have to look at the return temps. And typically when we get down, I guess these are typically sized to meet around a 55-degree saturated discharge temperature. If we're looking at the 0% outside air, it comes out to be about only 5 tons of cooling that is needed in order to meet those space conditions. But then as you start to incorporate more outside air, you have to start taking into account these ASHRAE peak conditions. So in this case, you're now, I guess, since we're mostly worried about the latent load, since that typically adds the most, I guess, additional need for the air that has to be processed, we start to increase what our mixed temperature is. So instead of the lower return air temperatures, we actually have the higher mixed air temperatures, and the same 5-ton system will now only be discharging around a 60, 58-degree temperature, which isn't going to be taking out as much moisture and can also lead to a higher space temperature since we aren't getting those lower discharge temperatures into that space. And because of this, it can lead to some temperature and humidity comfort concerns within that space, even though we are only introducing that smaller amount of outside air compared to using 100% return. So if we look at sizing equipment based on specific weather conditions, in this example, we'll use the same 2000 CFM supply, but this time we're going to use 100% outside air. The same location will be Charleston, South Carolina. And when you do take into account higher amounts of outside air, you have to look at both the hottest design days and the I guess worst case dehumidification days. And so what this will do is it'll make sure that you're looking at your peak load capacity in both situations, since oftentimes if these RTUs are, I guess the way these RTUs are typically designed is that they're only worried about the sensible load in the space, since they're only looking at maintaining that space temperature. But if you look at this example, if we take the hottest design days, it'll be about 94 dry bulb and a 78 wet bulb. And we try to cool it down to those same 55 conditions, it comes out to be about just under 13 tons of cooling is needed to meet those leaving conditions. But then if you look at the worst case dehumidification days, we look at, I guess we end up having about an 84-degree dry bulb and an 80-degree wet bulb. And to meet those same 55 leaving conditions, you're actually just over 14 tons of cooling that's needed. So if you're only looking at the sensible load, you could end up with an undersized system because you aren't taking into account the latent load that is needed from all that humidity to still maintain those same space conditions or those same discharge conditions into the space to meet what is needed. And obviously this will be worse for more humid areas or more humid climates. And really, when you're looking at the design of traditional RTUs, you really have to take into account that additional latent load as you are introducing more outside air to meet those outside air ventilation requirements. So RTUs are not really designed for processing the outdoor air load, since once again, they are only looking at what those space conditions are and meeting that sensible space temperature. Some other reasons, I guess, other shortfallings for RTUs and trying to handle those outdoor air loads is that they have very basic controls that are designed to maintain or process a steady return air condition. The system is only looking at, is there a need for space heating or space cooling? It's not taking it's not able to take into account those varying outdoor air loads, since the outdoor air conditions are not going to be consistent even in the same day, let alone year round. Typical RTUs do have a smaller coil. They typically only have a 2 or 3 row coil, and it's not really sufficient to handle that latent load, since the air is not going across that coil long enough, or it's passing through too fast, so it can't really pull any significant amount of moisture out of that airstream. The next, I guess, shortfalling for these is they are a fixed capacity operation, which can lead to poor space comfort, and they have no humidity control. So since these are just a simple on-off system, they don't really have the ability to constantly handle the latent load or the humidity that is being introduced from those outside air loads, since if there isn't a call for cooling, there is not going to be any sort of dehumidification, since that the only real way that these traditional rooftop units can provide any dehumidification to the space is through a byproduct of the cooling process, just because it is cooling down to that saturation temperature, and then it'll cool down a little bit further to around that 55 leaving temperature before it discharges into the space. And so whenever that cooling isn't activated, there isn't going to be any sort of dehumidification for the air being brought in. So as I kind of hit on in the previous slide, the only way to combat humidity is to keep the coil, or keep the cooling coil running, which can oftentimes lead to overcooled spaces. So when you do have that increased outdoor air amount, you have to look at oversizing the cooling of the unit in order to make sure that you are able to still get down to that target 55 saturated leaving temperature off the coil. And typically the space doesn't need that much cooling, but in order to get any sort of dehumidification or make sure that the cooling is going to be activated more often to get that dehumidification or increase space comfort, then you end up having to oversize the system in order to get it to run more often. So oftentimes the outdoor air is being tasked to be handled by these traditional RTUs is more than what the standard units can handle. So when they do oversize those units, you have to start setting your space set point lower, which will lead to the system running longer in order to get those additional dehumidification, or keep that cooling running to get that dehumidification to the space. And now you're dropping the temperature below what would typically be comfortable for the occupants inside of that space. And oftentimes, like you can oftentimes see it in buildings during the summertime, where if you walk into a building, you can notice that it's really cold, which is mostly because these systems are running or overcooling that space to try to get that additional dehumidification or keep the moisture out of the air that is being brought into that space. So in the end, they're sacrificing the space temperature just to make sure they aren't getting that additional moisture to the space. So another thing with traditional rooftop units is that they are fixed speed and fixed capacity operation. We know that the outdoor air conditions for anywhere is going to be varying even throughout the day. So it's not going to be the same constant load that is being tasked on that traditional RTU. And since this is a fixed speed and fixed capacity, it's not able to, it doesn't modulate to handle those varying loads. So sometimes you'll get, it's very inconsistent discharge temperature with this fixed speed equipment, because you're going to be transitioning between the peak loads during the day, or even peak loads of different days compared to shoulder days where they're more mild and you don't quite need as much cooling capacity or even heating capacity. And this will lead to constant cycling of the units, since they are just the simple on off whenever the space is calling for heating or cooling. So on milder days, you do get a lower efficiency since you're not operating at the peak load, and the system will satisfy the space more quickly and will cycle off until the gains in the space are enough for another call for heating or cooling, and then it'll shut off again. So off to the right is an example of actually heating for a unit, and it's based on a cycling on and off whenever there is a call or a requirement from the space to have heating. And as you can see, whenever there is a call for heating, the discharge temperature increases significantly until the space is satisfied, and then it starts to drop down again until once again there's another call for heating, and then it cycles on again. So this consistent cycling on off to try to maintain those space conditions or will oftentimes lead to discomfort in the space since you aren't continuously discharging a consistent temperature into that area, or you're allowing it to, I guess, have some sort of swing since it's looking at a temperature range to make sure that it's maintaining in there. And oftentimes if people are around where this air is being brought into the space, it can be possibly discomfort or I guess uncomfortable for them since they might be getting blasted with either the 100-degree air in the heating or the 55-degree air if it's cooling. And then it'll just continuously do that throughout the day since it's not designed to modulate or maintain a consistent leaving temperature or anything like that. So with cycling units like this, efficiency ratings are oftentimes sacrificed since these are designed to only meet code minimum requirements. Since RTUs can be very competitive in cost, oftentimes it's the lowest cost option that wins the day. So they start sacrificing what I guess might be the end building comfort or a better design practice just to get these lower cost equipment, which then starts to sacrifice efficiency, even though it will still meet the minimum requirement for what that space is needed. And then lastly, with traditional rooftop units, typically size the cooling around a 400 CFM per ton to help prevent freezing coils or overcooling. This is a pretty typical rule of thumb, but this can lead to a lot of wasted energy once you start to increase the amounts of outside air being processed through the traditional RTU system. So for example, it can lead to increased blower energy usage. So if you have a space calculation that calls for 5 tons of cooling needed to satisfy that space to meet and you're using that target 55-degree saturated temperature to meet those comfortable conditions. Once you start to, if you look at providing say 50% outside air or 1,000 CFM of outside air in that same system, it will end up adding an additional 5 tons of cooling load that is needed for that system to handle. And that's just based on the 400 CFM per ton that we're trying to size it around, while also making sure that you're meeting those 55-degree leaving temperatures. So with a fixed capacity rooftop unit that you will have to add 5 tons of equipment capacity at 400 CFM per ton, you're now looking at 4,000 CFM just to maintain that proper leaving coil and not, I guess, to prevent freezing the coil or overcooling that space. And because you now have to increase the supplier CFM, you also have to increase the energy used by the blower, which can increase the motor horsepower that's needed. And as a result, you have essentially 2,000 CFM of wasted additional supply air being moved beyond what that space is actually needing. So looking at how RTUs deliver air to the space, you can oftentimes find or hear from occupants of buildings that the building is more comfortable when units are not operating. And that's because when the units aren't operating, you're getting less movement of that, I guess, conditioned air across you. And then depending on how that air is being introduced and where the occupants are, if you're by a diffuser, you're going to have higher levels of air volume going across your skin. So you're going to feel it more often, or I guess more heavily than if it's away from where the occupants are. But then once that rooftop unit is called on by the space, then there's a higher volume of air moving. And if it is being oversized to have that outdoor air load taken into account, or to have the cooling cycle on more often to keep the humidity level lower inside the space, then that's where more discomfort can be had, because you have a higher delta T due to the fixed capacity of the equipment. And this will also be shown or more obvious on milder days, where you're getting you have less load that the rooftop unit needs to be taken into account, because it's sized for the peak load conditions, but it's still going to be conditioning or operating at that same capacity. So you end up overcooling to a lower temperature than what you might on the peak design day. And then that's where even more discomfort can come for anyone that's inside that space. Another thing for traditional rooftop units is that it has very basic blower controls. They're not really designed to provide that consistent outdoor air delivery in a proper method. So typically you'll see they only have an auto or an on option. So an auto, the fans will only turn on whenever there is a call from the stat for either heating or cooling. And the problem with this is that when the space is satisfied, then that fan will no longer be running, and then you're not going to be getting that outdoor air brought in to the space to meet that ventilation requirement. And then it'll cycle on and off based on whenever that space is unsatisfied or looking for the heating or cooling to meet the space temperature. Then the on condition, the fan will be running continuously, and there's no way to dehumidify when the space temperature is met, since it's only looking at that space if there's a call for cooling or heating. And if the space is satisfied, the fan's going to continuously run, and it'll bring in the unconditioned air at whatever those intake air conditions are, because it's not actually looking at the intake air conditions. It's only looking at the space temperature or the return conditions to make sure that the space is satisfied. So oftentimes, if it's just on, it can be bringing in unconditioned, humid air to the space that will eventually lead the space outside of the desired conditions, and we'll have to cycle the unit then on heating and cooling. So with the traditional rooftop unit approach, there can be some indoor air quality challenges, since we are bringing in very little amounts of fresh air ventilation, and they're only being brought in when that space is calling for heating or cooling, since majority of the time these units do run in the auto position. So whenever that fan's not on, you're not getting that outdoor air ventilation, and the space will, I guess, only be basically be stagnant until there is a call for cooling or heating. The other thing with them is that they usually have a very low level of filtration, since the typical RTUs only have about a MERV 5 filter that is used. And then the air is only going to be filtered when those fans are operational. So anytime that the fan is not running, that air inside the space is not getting filtered, even if it is just return air. Whenever the unit's off, that return air is just going to stay in the space, or I guess that space is not going to get, the space air is not going to get filtered through that unit. And then that can lead to higher levels of contaminants within that space. Some rooftop units, you can try to increase the filter efficiency for existing systems, but oftentimes they are limited by the fans and motors. because these units are not really designed to handle the higher static, especially if it is an existing system. Typically the highest efficiency filter you can incorporate into these is around a MERV 8, just because anything above that, the units can't handle the higher added static pressure from the higher efficiency filters. So with traditional RTUs, you can run into some building pressure issues, since typically these use just a basic economizer damper, as shown on the right side here. And a lot of times these are just a basic sheet metal damper that can be screwed into place, and then you can manually adjust it to bring in more or less outside air based on what is needed. But one issue with this is that if there is a system that is not designed to handle higher amounts of outside air, or if you end up bringing in more outside air than the system can handle, you'll find that on peak days, the system starts to underperform and you're not actually meeting the space needs. And this can lead to techs or someone coming out to look at the unit to address any issues. But oftentimes they'll find that the unit is operating as it's designed. It just can't handle the higher amounts of out air on those peak days. So they can end up shutting that damper more, which can lead to building balance issues and eventually have the space go negative, since whenever there's outdoor air, there should be some sort of exhaust or relief that is incorporated with that outside air to maintain that building pressure at that proper position. So if those dampers get closed, then the space ends up going negative, which can lead to infiltration and untempered air being brought into the space through other means, such as leaks in the windows, doors. And the issue here is that air is going to be untempered and unconditioned, so it's going to be humid air at whatever those outdoor air conditions are, which can lead to other ventilation issues or indoor air quality issues. So even on higher, current or higher accuracy building balance dampers, or newer building balance dampers, they still have a fairly low level of accuracy when you are using those lower amounts of outside air for the systems. Because even in the current dampers that are used for many RTUs, there's still a fair amount of play in those dampers when they're in a fixed position. So I'll play this video here. And as you can see, even when the damper is supposed to be in a fixed position, you still get about a 1 inch of play that can affect the amount of outside air that's being brought into that space, since that 1 inch can be quite a big difference in how much outside air is actually going through that unit. So trying to dial in these dampers to the proper amount of outside air to maintain that proper building balance is still going to be very difficult, since even current class 1A balance dampers can have this much play, since majority of the time that low leakage is just for when they're shut and not necessarily for their accuracy while they're open. So another thing with typical RTUs, or I guess with any equipment, is you have to have routine maintenance. But oftentimes with the traditional RTUs, they do have lower end components, since they are a very competitive market and you have to try to win the job by having the lowest cost available. But with these lower end components, it does require additional maintenance or additional equipment or component changeouts, because they are more likely to fail. So oftentimes with RTUs, you'll see that they are belt drive units, and belts are a very common point of failure. And everyone, I guess, we all know that belts have to be routinely maintained, either checked for proper tension or if they are slipping at all. And typically they're going to have to be changed eventually. And then the problem with this is when they do have to be changed, then the unit will end up being down until either the proper parts can get out to site, or if they need to get a service contractor out there, oftentimes it's going to be a third-party contractor or a third-party service that has to come out and service that unit, since most manufacturers don't have their own dedicated service team. Another thing is that any sort of remote monitoring or BMS will have to be done by an external party, and there's very limited access to these, or very limited options for what can be used on these RTUs. So getting into the economics of RTUs and kind of hitting on the previous points we've talked about, that can lead to a lot of wasted fan energy from having that increased outside air CFM on the supply, which leads to the higher supply amounts needed, even though the space doesn't necessarily need those higher amounts of supply air. Oftentimes we have a lower EER operational efficiency, since these are associated with the lower end components to help keep the cost down. The lower end components can also lead to the shorter equipment life. And one thing to keep in mind is that the compressor lifespan is rated based on the total number of starts and not the hours of operation. So with traditional systems, you're getting a lot more starts and stops compared to a continuous operation. And the reason that they're rated around the starts is because the most taxing part of the compressor operation is the starting and stopping of it. Oftentimes these rooftop units are treated as a commodity, and it's not uncommon to expect them to have to be replaced in under 10 years. And whenever having to look at replacement costs, it's not limited to the equipment itself. You have to start factoring in costs for cranes, running the new electrical, the gas connections, and any curb adapters that will be needed for the new equipment. And then if you ever look at increasing the warranty on these to get a longer lifespan out of these, it can be very costly to upgrade that warranty. So here's a section from a fairly major RTU manufacturer. And in the manual, it actually states most HVAC units are not designed to handle high quantities or high extreme conditions of outdoor air. And that kind of drives home that even these manufacturers know that traditional RTUs are not really designed to process those outdoor air amounts. And then they also say that oversizing a traditional HVAC unit to handle the high heating and dehumidification loads of outdoor air can result in poor control of zone air temperature and humidity, leading to poor occupant comfort. So all these challenges that traditional RTUs face is actually a very, very well known and very common in this system or in this industry. So it's best to not have the traditional RTUs handle these outdoor air loads. So you can even look at how these systems are tested. These RTUs are tested to the AHRI standard, and it's designed primarily around 100% recirculated air. Some may claim that their systems are able to handle or able to process higher volumes of outside air, but realistically, these are designed to meet the minimum code requirements, which is based around the 100% outside air. And there's no real way to verify that these RTUs were tested around these outdoor air loads or at what cost might be needed to handle these and process this outside air load. So in summary, RTUs can lead to low comfort, both in temperature and humidity control. They can lead to poor indoor air quality from using less fresh air, or I guess lower fresh air amounts being brought into the space, or even cycling that outside air so it's not continuously being brought in. They have the lower grade filtration, and they oftentimes use the high volume of recirculated air. These often have lower efficiency while having higher operating costs, just because they are using the lower end components that are in the fixed capacities, and they aren't really designed for a sustainable life or lifetime operation. And there's no, I guess, very few monitoring options to make sure that these units are operating effectively throughout their lifespan. So getting into this, or I guess transitioning into the DOAS theory, or dedicated outdoor air theory, is to essentially move away from having these traditional rooftop units handle this outside air load. And this is starting to become more common as more modulating components such as VFDs are becoming more readily available. And the theory is basically to have 100% of all outdoor air being delivered to a building to be processed by this DOAS unit. So this will allow the RTUs to only worry about that indoor sensible load or the return air from the space, while the rest of the outdoor air and ventilation is handled by these DOAS equipment. So why would we look at using DOAS for this? That's specifically because DOAS units are designed around processing higher amounts of outside air loads. This is helpful, I guess, done through all these modulating components, so they are actually designed to be able to handle the varying outdoor air conditions throughout a day-to-day operation. This will allow an increase in efficiency for the building HVAC system, since it will decouple the latent load from the sensible loads. It will simplify the RTU design, and then it'll also allow them to, I guess, be sized smaller, just since they're only handling that return air load and not any outdoor air loads. It'll allow for better air distribution throughout the building that they're serving, and then you're guaranteed humidity control and improved comfort. So a typical DOAS building design paired with an RTU unit will have the DOAS handle the outside air load to maintain a neutral discharge air temperature and humidity, while the return air units or the rooftop units will handle the rest of the space conditioning. So the DOAS unit will only handle those outside air loads, while the RTUs will make sure that the space is at the desired comfort level. And that helps kind of take the load off of those rooftop units. So a DOAS unit can also be used as a primary source of space comfort and ventilation. So you can use return air with DOAS units, and they are still able to handle that mixed air condition, since they do have the modulating components, and they can be used to temper the air to maintain a proper space temperature and humidity, since they are designed to handle more of those outdoor air loads and look at maintaining the humidity or the dew point inside the space rather than just the temperature. So how is DOAS different from the traditional RTU coil or traditional RTU design? They do use wider coils, so the air has a increased residence time, which will allow for more moisture removal. So one of the primary uses of DOAS units is to reduce the humidity of the air in the space or being brought into the space. So these will actually look at monitoring both the temperature and the relative humidity or the dew point of the air being brought in or even in the space itself. And then it can use any sort of combination of outdoor air, mixed air, return air, and then it also monitors all of these different conditions, both at the intake, the return, at the discharge of the coil, and at the space. And then very commonly, DOAS units will also have modulating hot gas reheat to actively control the humidity while making sure the space comfort is also maintained. So looking at a brief psychometric chart of the DOAS operation. So you are looking at in this case, a 100% outside air unit. You'll only be taking into account those outdoor air conditions. And then you actually will condition those still down to the leaving coil temperature of the 55 discharge off the coil. And then after that, the unit will actually use the hot gas reheat to condition that air back up to a more comfortable space condition, while also making sure that it is dehumidified air in the space. So DOAS units also have the modulating capacity and variable speed operation, which will allow it to work in a variety of outdoor air conditions. So it's actually able to modulate the output of what this unit is operating at. So as we hit those shoulder days, or as throughout the day, if you have lower peak loads, the unit will modulate to make sure that discharge temperature is consistent along with the dew point if we're worried about the humidity or dew point in that space. So as you can see here from one of the monitoring of our units, the compressor speed will vary while the outside air temperature is slowly decreasing, but that discharge temperature is maintaining fairly constant. So a variable speed compressor versus a single stage compressor. Variable speed will slowly modulate down based on whatever the cooling need is for that space or for the air being brought into the space, whereas a single stage will just be the typical on-off for it. So as you can see here, for traditional RTU in the purple, it's cycling on and off consistently, while the DOAS unit in blue will just be operating throughout the entire day at whatever capacity is needed to maintain those space conditions. So even with the adaptation of modulating equipment, the outdoor air is still the most expensive air in the building. And so efficiency is very important. And that's because the outdoor air conditions are going to be widely ranging and much higher, or require much higher loads to process than just the standard return air conditions. So a lot of the equipment will have an integrated efficiency rating, or the IEER, which will allow it to catch up and lower component costs. So that takes into account more than just the peak load operation of, I guess, units. It's actually looking at the shoulder days and the modulating efficiency of those throughout the operation. And what DOAS units will oftentimes use is a true inverter duty variable speed scroll compressor. And this is what allows it to, I guess, a modulating compressor versus the simple on-off. It will have ECM or other direct drive blowers that will either use the ECM or VFDs to modulate the supply air speed. And then it will also use electronic expansion valves versus the simple thermal expansion valves. So this allows for us to process outdoor air with lower energy costs. Another benefit of using DOAS units is that it will improve the indoor air quality, since you are bringing in more outdoor air into the building versus using higher amounts of return air. And this also will allow for improved air quality, since DOAS units typically have a much higher filtration rating compared to standard rooftop units. Typically, the minimum MERV rating for DOAS units is around a MERV 13, but these can be upgraded to a MERV 15 or a HEPA filters. And traditional RTUs with belt drive blowers aren't going to be able to handle that additional static pressure. So that's why they are, I guess, kind of limited to the lower MERV 8 or MERV 11 filters that they're traditionally used with. So getting into the DOAS economics, DOAS relies on the latest technology using the high efficiency and modulating compressors and other components. With all newer technology, over time and higher adoption rates, the previous challenges are going to be avoided. And as they become more common, the cost and reliability will slowly be improved as well. So with variable speed technology being more readily available, it increases the reliability and sizing options available, while also driving costs down and making sure that efficiency is improved in the long run as well. So rooftop unit prices will continue to rise as code minimum requirements continues to raise as well, along with efficiency standards. So even if they are still being designed around those minimum requirements, then it's gonna require additional RTU components or improvements that will also increase the cost of those. And as more options are being added to meet those needs, such as hot gas bypass, economizers, you're once again going to be increasing those costs as those requirements or even those standards are being met. And then high-end components aren't used in RTUs, so throughout the lifespan, the RTU equipment is not going to be lasting as long as DOAS units, which use these higher end components that are becoming more readily available. Another offset of costs for DOAS units is that they are able to use a smaller ductwork, since you aren't having to oversize the units or account for the higher amount of supply air that might not be needed for the space. You can lower the tonnage on the rest of the RTUs that are serving the space so they don't have to be oversized. And then you can remove the expensive economizer option for traditional RTUs, since that DOAS unit is going to be what is handling all of that outdoor air load. So another thing with DOAS units is that the introduction of ERV or energy recovery can be introduced. Oftentimes this is done through a wheel as shown here. Oftentimes ERV is used as a tool to reduce the energy usage of DOAS units. So what it'll actually do is it'll take return air through the energy wheel and essentially condition that wheel so that some of the load is taken off of the DOAS system, since it's now going to be looking at almost preconditioned outdoor air, or air that is going across that wheel is now going to be slightly, I guess, conditioned so that there isn't as much cooling or heating needed from those when the DOAS is operating. These do have a higher upfront cost and install cost, and all ductwork then has to be run through a single return back to the ERV module. But as DOAS equipment efficiency increases, the paybacks will also be harder to maintain as they offset the energy costs will go down. So right now ERV is common because DOAS, I guess, efficiency is going to be slowly increasing, or I guess not quite as efficient as maybe it will be in the future. But as the DOAS equipment does increase in efficiency, the need, or the, I guess, payback cost from having ERV is going to slowly decrease. So ERV does rely on many factors for if you're getting any payback or if you're getting any benefit from incorporating this ERV, such as the efficiency of the DOAS equipment, having the proper sizing of DOAS tonnage to offset that ERV operation. Proper maintenance for the filters and for the wheel to be cleaned is going to be very important in maintaining that ERV operation. The advanced ERV logic is going to be a little bit higher cost to actually make sure that the ERV is operating to reduce any energy usage. And then there can still be some air quality concerns from potential air either bypassing the exhaust or even contaminating that wheel, depending on the application, which would then get into the airstream. So how do you make sure that you have a sustainable indoor air quality? Some simplified controls is one of the major important steps to make sure that you aren't trying to overcomplicate the operation of the system. Having proper startup and commissioning of the system will always help make sure that the unit is operating as it needs to be. Ensuring that there's proper maintenance and service throughout the lifespan of the system to ensure, once again, that it is continuously operating where it needs to be, and then also continuously commissioning that system to monitor where that operation is, and so that it's not operating outside of the bounds. So with simplified controls, it helps reduce any of the complication that might come from having a very sophisticated or complex sequence of ops when the space might not need a very complicated sequence. Oftentimes this can lead to complications with incorporating that sequence or making sure the space is maintained where it needs to be, just because there's some miscommunication on how these controls are being introduced or incorporated, and it just requires a lot more intricacies or interlocking between multiple manufacturers or multiple control systems to get that level or get that complicated sequence of ops to where it needs to be. So in a lot of cases, just keeping it simple is going to be a surefire way to make sure you are achieving the desired outcome without getting into too much complexion. So another important aspect of DOAS units, or any unit in general, is the continuous maintenance and service of these. Since DOAS units are exposed to a wide variety of outdoor air conditions, you have to continuously monitor how the unit is operating to make sure that it is meeting those space requirements or those discharge air requirements. Another thing with, operating around more outside air is that it's a lot more critical to service the filters, the coils, the heat exchangers, since that outdoor air load and any contaminants from outside can put additional stress on components and shorten their lifespan. And it can also end up causing the unit to operate outside of where its design is, such as if the filters are dirty, you're not going to be able to consistently have that same supply air through the system unless those are changed or cleaned on a consistent basis. It's important to have factory trained personnel or factory trained service techs out to service this equipment so they can make sure that any repairs or alterations are done properly. And then parts availability is also important for any unit, since the repair can't be done on a unit until those parts are on site. But that's a similar concern for any RTU or equipment in general. So one benefit of our DOAS unit is the continued commissioning that is available through remote monitoring. You actually have the ability to have real-time alerts for any issues that occur, and you can see the continuous operation of the unit for what kind of temperatures it's discharging to the space or what space conditions it's actually able to maintain. It allows the manufacturer's engineering team to assist with real-time repairs or real-time monitoring to address any issues that come up. And then you can also review any data that leads up to faults to help diagnose what might be causing any of these issues or what steps need to be taken to correct these issues. So they also allow for fine-tuning the equipment for maximum comfort and efficiency. So you can actually save a trip, like a service call trip, since these can be done remotely. If the customer or end user is saying that it's too hot or too cold in the space, then you can actually remotely do that rather than having to send out a service tech or call in a service tech to go and make that change on site. And then you have guaranteed performance, since you're able to verify that the system is operating as it's intended, and it ensures that the outcome isn't just met, but it's also consistently being maintained. So if you're looking at a traditional lifespan of a unit during the design phase to all the way to when it's out in the field, you can see how the unit is operating. And oftentimes it's after the warranty period has expired that you start to see specific failure points, and it becomes more likely that units are going to fail or start operating as they aren't needed. But when you do have, or I guess outside of where they're needed, but when you do have continued commissioning, then it becomes a lot more consistent, since you're able to consistently monitor how that unit is operating. And even though over the lifespan you might have some component failures, you're able to see where it might be happening or quickly address what is causing the unit to operate outside of its desired bounds. And you can continuously do that throughout the entire lifespan of the unit, not just until the warranty is over or once it gets on site, or have to worry about word of mouth if someone on site is saying one thing, but when you get out there, something else is going on. You can actually see right away what is happening or what happened at a specific time when the unit went out of its proper operation. So, like I mentioned, oftentimes, if without having this real-time monitoring or diagnostic ability, by the time the call comes in to when it's addressed or when a service person can get out on the site, it either might have fixed itself so that they can't recreate the issue, or it's back to operating as it should be, and people are just scratching their head, we don't know what happened or what changed, but earlier the unit wasn't operating as needed. So you can see with the real-time monitoring what exactly occurred and see why it might have happened, so you can address it to prevent it from happening again in the future and avoid any back and forth on every time, like during this time of day, we always have this issue, but we can't make it happen later in the day. You can see why it's having that issue ahead of time. So this also allows for verified operation, which is very important for critical applications such as clean rooms. You need to make sure that there is a consistent space temperature and dew point being maintained at all times. You can't really have it varying out in and out of the space requirements throughout the operation of the unit. So having this real-time monitoring ability will help make sure that the end user is satisfied, and that if it is a critical application, anything inside that space is not going to be affected negatively or have any issues because that space is not consistently being maintained where it needs to be. So with sustainable performance, we know that we have the tools available to effectively maintain peak building comfort and performance throughout the operation of the unit by using DOAS units in conjunction with any RTUs that might be needed to handle these space loads. And we also have the ability to consistently make sure that the units are operating as they should be to maintain that optimal building comfort or building set points. So the final outcomes of indoor environmental quality by using DOAS units is you'll have the continual supply of fresh and filtered air being brought into the space at the highest level of indoor air quality is maintained, so that the highest level of indoor air quality is maintained. Your building comfort and health dramatically improves with modern DOAS technology compared to the old style rooftop units. And then DOAS units also provide precise control over the temperature comfort, the humidity control, building pressure, while also ensuring that the indoor environmental quality is maintained. So in summary, outdoor air should be used through DOAS units. The only way to prevent mold and humidity issues in buildings is through the use of DOAS technology, since they are designed to handle those outdoor air loads properly and precisely condition the air being brought into the space. And bringing hot and humid air into the building in the year 2021, 2022 should not be done, since we have the technology to avoid it. There's no need to continuously face those building challenges and go down the route of not having the high indoor air quality. For any questions, feel free to email myself or Western Reserve, and we'll get back to you on whatever you might have. Other than that, thank you everyone for your time, and hope you have a good rest of your day.